All right, I think you can start.
Good. Okay. Then let's see if it works. Okay. Can you see the presentation?
Yes.
Good. Okay, then I start. Thanks for being here. So as I already said, I'm going to talk about the effects of climate warming on slope instability and debris flow activity in a high mountain region of the Italian Alps. So, okay. The main question that we are asking is if is slope instability and related hazard increasing due to global warming? Of course, we are not the first to ask these questions, and there are many papers that have already tried to analyze and try to ask exactly the same question, as you can see, for example, here. And so there are, at least in European Alps, there have been many studies that just developed after the hot summer of 2003. After which many landslides, many rockfalls have occurred in the whole Archean Alp. You can see here some location where publications and studies have been made, and just some of the names where you can find more literature. So the point is, why are we still asking the same question if already all of these studies have tried to answer it? Well, there are some problems which can be grouped into two categories. The first is related to the timing. So basically, the rock avalanche and slope instability can only be either indirectly and to temperature increase. Temperature increasing is directly affecting the glacier retreat and the melting of permafrost, but then there is some time passing between these effects and the debris stressing or the thermal stress and frost cracking action that actually create the failures. So failure can occur years to millennia after the climatic change. And there are some researchers, for example, who claim that the very large landslides and rockfalls that we are observing today in the Alps are still related to the warming of that occurred at the end of the Little Ice Age. Then there is another problem, which is related to the space and more specifically to precipitation. So precipitation are supposed to increase because of global warming, and especially increasing in extreme events. Therefore, we can have a direct consequences with an increasing river discharge or an acceleration of soil saturation, which can then trigger landslide and debris flows. However, precipitation are very difficult to predict and extremely variable in space. And therefore, it's very difficult to link a landslide or a debris flow with a precipitation, and especially it's difficult to make prediction on how this will change in future. So to answer this question, we look at the landslide scars and analyze their spatial temporal evolution in comparison with the geology and the geomorphological domains of the catchments and with temperature and rainfall data. In order to avoid the problem related to the timing, we only looked at small to medium-sized landslides because these are the landslides that can be directly linked to temperature variations and normally occur with a very short timing after the perturbation, the climatic perturbation. So we excluded all very large landslides and landslides or mass movement that can be related to, for example, debris stressing. And then we also look at the debris flows events and try to understand how they enter in the big picture of the climatic warming. Finally, we look at how instability has changed in both space and time and try to relate these changes with variation in the hazard or risk probability. So our study site is located in the central Eastern Italian Alps in the South Tyrol region, and is called Sulden catchment to the north. So in the south, we have glaciers, which are these light blue color here. The catchment ranges from a low elevation of 1,300 meters, which is here at the outlet, and goes up to 3,900 meters, which is the top of the Ortles peak, which is the highest mountain in the region. It belongs to the Ortles Civedale group, which is a very famous and touristic place here in Italy, where many climbers, many hikers go to reach especially these two peaks, the Gran Zebru and the Ortles. Okay, so sorry, go back one slide. There are two weather stations in the catchment. One is located at the Sulden village at 1,900 meters, and one is located higher up in the catchment here at 2,800 meters, and it's called Madrich. This is called Sulden, this is called Madrich. You can see here the temperature and precipitation data relative to these two weather stations. So for temperature, you see these graphs, which is showing the mean annual air temperature for between 1955 until 2019. And you can clearly see that starting from the 1980s, there has been an increase in temperature at both stations. And if we now look at the lower panel, which is showing you the linear trend in different seasons, where you have a summer, spring, fall, and winter, and the dashed line represents the Madrich station, so the one located at the higher temperature. You can see that temperatures have been increasing in all seasons, especially in summer and spring, which are the dark colors, and has been increasing more at the higher altitudes. These numbers here in the lower part just give you the average conditions, so for the mean annual air temperature and for the mean annual precipitation at both the location for this time period, 1981-2010. Now the graph of the precipitation, I just want to point out that, so this dashed line represents the average that you can see here for these 30 years. And then you still have the yearly mean annual precipitation. The Madrich station only started to register in 2009, and that's why we have only data in the youngest years. And what you can see from these graphs is that there has been a period between 1995 and 2010, in which the mean annual precipitation have been lower than average. And then in the last 10 years, this precipitation have increased again. With this arrow and with this time period, I just show you the time periods where most landslide and debris flows have occurred in the catchment and have been registered by the local authorities. So this is just to keep in mind for the next slides. Also, the lower panel show you the seasonal trends with the same color that you have here. So you see that precipitation have increased in all seasons, with exception of summer, which show a quite slight decrease. Good. Next, we look at the rainfall events. So these are defined based on some thresholds and on the relationship between duration and intensity. There is a code, a MATLAB code, which allows you to do this calculation. You just have to define the threshold that you want to use. And for example, we established here that rainfall at a minimum threshold of 5 millimeters, and 2 different episodes of rainfall could be calculated if there were at least 6 hours without rain between the 2 events. So all of these dots represent the rainfall events for the period of which we have data. And we have compared these rainfall events with the occurrences of debris flows that we have for the catchment. And you see that the rainfall events that were able to trigger debris flows fall in a very specific range of duration and intensity which is above this dashed line that represents the 75 percentile of the entire distribution. So we can say that for this catchment, precipitation events exceeding this threshold of 75 percentile may be able to trigger a debris flow. This is also an information to keep in mind for the next slide. Good. Then methodology. Basically, we mainly use the orthophotos, which are available for the catchment starting from 1945 and up to 2019. These orthophotos allowed us to map more than 1,000 detachment points for shallow landslide. So with detachment points, I mean the landslide scars. So the point location where that we detected as a starting point for a landslide. Then we used several available information like the geomorphic map of a study site, a map of landslide events occurred in 1987, then the natural hazard database of a Bolzano province, the distribution map for permafrost. We applied the frost cracking model made by these different authors, and also applied a theoretical model for snow cover effects on slope instability. And of course, we look at the available climatic data about temperature, precipitation, and snowfall. Good, I'm going to the result. In this map, you see all the detachment points that were detected from the orthophotos. The different colors show you the different time frames for which we had the orthophotos available. And you can see that, for example, the oldest one, of course, cover a very large period, 40 years, because we had no orthophotos in between. And instead, we have more orthophotos in the recent times. In the background of the image, you see the permafrost distribution map. That is just the probability of finding permafrost. Next, we look at the elevation of all of these detachment points divided by years. So the colors are the same as of the previous images. And you can see that the elevation of the detachment points shows an increase in trend. And this increase in trend also is reflected by major probability of finding permafrost in the younger years. And then this is quite obvious because, of course, permafrost and elevation are related. So the higher we go, and the higher is the probability of finding permafrost in the slopes. There are two exceptions to this trend, which are the same time period that I showed you before, where we have many landslide and debris flows occurring in the basin. And also here is the same exception. Next, we look at the geomorphic map. This is just simplified geomorphology map of the catchments, where you can see the main cover types and then geomorphic processes area. And we look at where the detachment points were located in comparison to these geomorphic domains. So if we consider the full data set of the detachment points, we have these graphs where you can see that most of the detachments were located in rock pools and bedrock. So I put them together. This is just a division that was made on the geomorphic map based on slope, but we can consider the two things together. Basically, these light colors show you all detachments that were located in bedrock, and then decreasing the areas with major detachment points. So there is an area with diffuse erosion, shallow soil, debris cover, slopes, talus slope, and debris flow channels, and then all the others. Now, if we do this same exercise, but dividing the detachment points for the time frames, we obtain these other graphs, which is a bit complicated, but I'm going to explain the most important things. So you basically see that for all time periods, almost all time period, Still, bedrock and rock wall are at the first place in terms of number of detachments. And again, you can see that there is an exception, which is again related to these two time frames, where we had many landslide and debris flow related to the precipitation, to the high precipitation. So there is already some conclusion, a preliminary conclusion that we can draw from this analysis. So we can say that mass movements which are linked to rainfall events mainly occur in shallow soil, zone of diffuse erosion or debris flow channels, and they do not show any particular trend in elevation change. Then there are some mass movements which are not linked to rainfall events, and they mainly occur in bedrock, and they show clear increasing in the elevation of this detachment. So we went a bit deeper into trying to understand what was this link. First, looking at the mass movement which are connected to rainfall events. Now in these graphs, you only see the rainfall events exceeding the 75 percentile of the duration intensity distribution, because we are seeing that these are the events which may trigger a debris flows or a landslide. You see that they are concentrated in the summer months, in spite of the fact that we have a decreasing trend in precipitation or in the summer, but still the highest intensity events, so the most extreme events, occur in summer. And then you can see in the lower panel, this is a distribution of the rainfall events in the different years. And you can see that they reflect quite well the distribution of a precipitation of the mean annual precipitation. And I'm meaning that there is a this time period between 1995 and 2010, where mean annual precipitation have been lower than average. And you can see that also the number of these extreme events was quite low. And then we have instead a major number and an increase in the last 10 years, which also reflect the increasing precipitation that we register in the annual time frame. And with the arrows, I have pointed to the major and minor debris flows that have been registered in the catchment. With major debris flows, I mean that during some specific precipitation events, many debris flow channels and were activated with debris flows, and also many landslides occurred in the catchments. And with a minor debris flows, I mean that maybe only one or few channels were activated during these events. So what about the mass movement which are not linked to rainfall events? Well, we suppose that they are linked to temperature variations. And in these graphs, you see, for example, the number of hot days registered for the time period in which we have daily temperature measurements. Hot days are defined based on this relationship. So when the daily mean temperature is above the 95 percentile of the mean daily temperature of the analyzed time period, this is defined as a hot day. And you can see that moving from the 1980s to the last decades, this number has increased a lot, and especially at the high altitude. There has been a big step, a huge step over the 2000s, where the number of hot days are more than doubled, so almost 3 times higher. And now if we look at the number of detachments that we have registered for the same time period, you can see that there is quite a good correspondence and a quite same increase, where, for example, the number of detachment points is almost a double between the 90s and the 2000s. So we could speculate, or we could affirm that these detachments are somehow linked to temperature and to temperature variations. So next we could ask, how may temperature affect slope stability? We have looked at three main aspects. One is permafrost and permafrost melt. One is the frost cracking action that act exactly on bedrock, which we have seen that is the major source for instability. And then we look at the snow cover effects. So regarding permafrost, I've already showed you before these graphs. Again, you see the elevation change, this increasing trend in elevation towards the younger years, which is reflected by this increasing probability of finding permafrost. However, this is just probability map. So we add some evidence in the field about presence of ice in landslide scars, but of course, this is not verified for each point. However, for sure, permafrost has an effect on the slope stability. Next, we look at the frost cracking model. And this is just performed in bedrock. So these black lines represent the bedrock outcrops. And we look at how the detachment points were affected by the frost cracking intensity. And this is the graphs that we obtained. Now, this was quite surprising because I was expecting to see an increasing trend in the frost cracking intensity going from the oldest period to the youngest one. But instead, you see that there is no clear trend, and the average data are basically all in the same line. However, then we look at the depth at which frost cracking is most intense. And we have seen that basically the most intense frost cracking always occurs at the surface. So within the first 20, 50 centimeters. So this means that the increase in temperature is shifting the elevation at which frost cracking may act at the surface. And that can be one reason for which we observe an increasing in detachment points in shallow landslides at higher elevation. In fact, if we look at how frost cracking is influenced by temperature for this catchment, we see that there is a very big step, when the temperature, air temperature passes from -1.5 to -2. The depth at which the most intense frost cracking occurs jump from the first 20 centimeters down to 2.5 meters. So if we now plot the temperature range that allows the frost cracking to act at the surface, so between +4 and -2, and we plot it against the location of the detachment points, you see that there is quite a good correspondence. Especially if we look, for example, in this part, which is a zoom in of this area. You see, for example, that this slope here, which has temperature that are too cold to allow frost cracking to occur, present no detachment points in spite of being very steep. And also this area instead, which has the temperature in reality to allow frost cracking, also showed no detachment points. But what you can observe is that it is very shallow portion of bedrock, and therefore this can have something to do with the effect of snow cover, which I'm going to show you next. Good. Okay, how does snow affect frost cracking? Here, this you see, it is an annual cycle of temperature. So the lower portion represents the winter, and the upper portion represents the summer. So these are just days in 1 year. And here you can see at the surface temperature of +3, so a quite low elevation, which could be in the catchment around 1,900 meters, for example. You have frost cracking acting during winter in this portion that is colored with a pink. And you have here the maximum intensity of frost cracking in the first 1.5 meter of depth. However, if we add snow cover, so if we have snow cover which is with a thickness above 60 centimeters, we know that this insulates the ground from thermal variations, and therefore frost cracking cannot occur. If we now add the duration of a snow cover to these graphs, you see that basically it cancels the effect of the frost cracking. So frost cracking is not occurring at this lower altitude when snow cover is higher than 60 centimeters. If we now do the same exercise for the lower temperature, that means higher altitude, we see that the effect of frost cracking mostly occur in summer, and this would be the depth at which most intense frost cracking occurs when there is no snow. But if we add the snow cover and think about the snow cover which has a thickness above 60 centimeters, this is what happens. So the frost cracking effect is strongly reduced because it can act only in these windows where we have no snow. And also the depth at which most intense frost cracking occurs is much deeper. Then a snow cover can also act in another way. So during melting, for example, the snow melt is going to increase the hydrostatic pressure in the bedrock, in the terrain. And here is just a representation of the Driving et al. Model based on the data of our catchment. So the blue line represents the average snow height in the catchments, and this gray background represent the instability windows that they calculate based on this snow melt period. So in average snow cover conditions in the catchment, in the Sulden catchment, we have instability windows related to the snow melt, which goes from May to July. This is an average condition. That means we draw this curve using the old data that we had at disposition for snow measurements. However, then we have differences depending from year to year. For example, 2007 had a very low snow cover, and therefore we had a lower effect of protection from the thickness of a snow cover, and a major increase of these instability windows, which you see was much longer because of the snow melt was very long, going from April to beginning of June, but also some other instability windows in late winter, early spring, and then in December, which were related to freeze and thaw cycles. And for example, this could be one reason for which we had very high number of detachment rate in this time period. The same high number, so we also had a very high number in the last analyzed time period, 2019 and 2018, 2019. But this instead could have been related to the very high snowfall, which occurred in 2019 and occurred in a very late spring. So most of the rainfall between April and May, it fell almost 3 meters high of snow at the end of May. And then there was a sudden increase in temperature in the beginning of June, which caused a very high, very fast snow melt. And this may have created a fast increase in hydrostatic power and created a very strong stress in bedrock, which could have been then resulted in this very high number of instability. So just to summarize this very long speech, snow can affect slope instability in mainly two ways. When snow thickness is above 60 centimeters, it strongly reduces or eliminates the force cracking action. However, we can have an increase in pore pressure when the snow melts, especially if we are in already partially frozen grounds so like under permafrost conditions or during very fast snow melt periods. Good. By just arriving almost to the end, we can say that slope instability is linked to global warming. We have registered an increase in temperature of circa 1.5 degrees from the 80s to the last decades. And at the same time, we have registered an increase of 300 meters in the elevation of the detachment points. However, slope instability is also linked to precipitations, especially for this catchment, rainfall exceeding the 75 percentile of the intensity duration distribution may be able to trigger debris flows. And we have seen that there has been an increase in the frequency of debris flows in the last 10 years. Then we don't have to forget the possible cascading effects. So basically, we have seen that the increase in temperature is shifting the region where most superficial frost cracking can act, and therefore is increasing the elevation at which we have the generation of a shallow landslide. This results in an increase in sediment supply at high altitude. Then this sediment supply may directly enter in a debris flow channel, for example, depending on the connectivity, or can be stored in temporary sediment sources like talus slope, or even inside the channel. And then, because we have this increase in the sediment supply at high elevation, we can have an increase in the mass movement, also lower elevation, like for example, the debris flows, when it rains. So we have more production of sediment at the high altitude, and because of these cascading effects, we can also have an increase in mass movement at the lower elevations. So in fact, we have looked at how these changes have occurred in the spatial scale. And now also this map is quite complicated. I'm going to explain it to you. So the very dark color represents the tributaries with the highest number of detachment points compared to the area of the tributary. You see that this portion here, which has very small tributaries, but which are very steep, they have a very high number of detachment points. And these are also the tributaries that mostly produce debris flows. And all of these other catchments or tributaries, which are much bigger, show lower density of detachment points. And this has been calculated over the full time period that we have analyzed. Next, we looked at how this density point has changed in time. And we compare the time periods 1985, 2003, 2003, 2009. And now this map shows you the changes, so in percentage, respect to these two time periods. You can see that the violet areas have increased their instability, so the number of detachment points, more than 200%. However, there are also some areas which have this greenish color that have become more stable. And you can see that by the location of these tributaries here, which are located in the lower portion of the basin, that this major instability is mainly related to recolonization of the vegetation and to the presence of forest. So all of these catchments have become more stable. Some of the debris flow tributaries here remain quite active, very high active. But what has really changed is all of these tributaries here, which show a very strong increase in instability. Now, as I told you before, we have an increase in the sediment supply at the high elevation, especially here where we have a glacier. You may see some black or very dark gray colors here, which represent the trajectories for rockfalls. And then you see this light blue color here, which represent the inundation areas for debris flows. So you see that all of these trajectories, for example, may end up on the glacier. And so they are going to contribute to the darkening of the glaciers, but they do not contribute to an increase in hazards at the downstream section because they are disconnected from the channels. However, there are some other areas, for example, here, where an increase in rockfall activity at the higher elevation may directly enter in the channel system and therefore may also increase the hazard related to debris flows when it rains. So to conclude, have we answered the question? Well, if we look at the instability, slope instability, I would say yes. Higher temperature, rise in number and the elevation of mass wasting events. But maybe it also depends on the site because depends where it rains. When it rains, we have an increase in the frequency of debris flows. And related to the hazards, is slope instability, so is global warming increasing the hazard? Yes, at high elevations. So we have an increase in sediment supply, and this may be risky, especially for tourists, hikers, and climbers. Maybe at low elevation because it depends on connectivity, and therefore is also site specific because every catchment will have to be studied by its geomorphology, morphology. However, there is in general higher potential for increasing hazard due to the increased sediment supply at the high elevation. And with this, I have finished. I hope I have been clear, and I am ready for questions.
Okay, so thank you very much, Sara, for this really, really interesting and amazing talk. We are now ready for questions. You can either write them in the chat or you can raise your hand using the little hand signal emoji, and we will unmute you. All right, so maybe just until to start things off, until some people type their questions, I will start with a quick question, and that is, it's a scaling question. Do you think this can be scaled further back in the past, so we can also learn about past events, past warming events, and look at how they affected landscapes?
Well, the problem is that, yes, I would say yes, but it depends on which technique you're going to use to evaluate the spatial variability in landslides. Because, for example, here we were lucky that we had very old orthophotos. Going more back in time, maybe it could be difficult to know exactly the elevation at which the landslide occurred. You may have a report of a landslide event or a rockfall event, but to really know the exact position at where it started, so really the scar, it may be more difficult. For example, we have now is in the same catchment, we are also doing some dendrochronology reconstructions to have an idea of the past debris flows events. But of course, this is a technique that allows you to date or to reconstruct the frequency of debris flows, but it doesn't tell you where the detachment occurred.
I guess I'm coming to this from the point of view of cosmogenic nuclide person, which is okay. We're always thinking about can we look at scars and date them and then see if we can connect them to past events.
Yeah, but, then with this technique, of course, you're really able to date the scars. So although with a cosmogenic nuclides you have a more wider uncertainty. But if you go back in time, of course, you can use it, yes.
All right, so I see we already have our first question by Goan Yu. He says, it's a very nice talk. I'm wondering the debris flow events in this catchment in recent decades. Is the frequency increased?
Well, that's exactly is what I was talking about. So at the moment for this study, we relied on the natural hazard database of the province, which started to collect, or let's say to register the events in 1997. It also includes very old and historical events, but of course, for the historical events, I believe that only the very large ones have been recorded. So there may be a gap or a bias towards the most recent times, simply because there were more observations. And that is exactly why we are also trying to combine a dendrochronology study for establishing the frequency of the debris flows, because with a dendrochronology, we are able to fill the gap between these two observation periods. So for the data, at the moment, the data that we have show an increase in the frequency in the last 10 years, but it could be that this increase is somehow biased by the most recent observations.
Perfect, thank you. Okay, so we have a next question from Daniel Drebing. He says, thanks for a nice talk. What do you think will happen when climate warming continues and frost cracking and permafrost regimes will shift to elevations above your mountaintops? Then your sediment supply would decrease and the hazard potential will be reduced.
Yes, this is very interesting indeed. Maybe. We have seen, for example, that we have a stabilization of the slopes in the lower portion of the catchments because of the recolonization of the forest and vegetation. So it is really possible that there will be a decrease in the sediment supply at the higher elevations and major stabilization of the lower part because of the vegetation. It would be interesting to estimate how long this would take. So if we consider, for example, the rate of increase in temperature that we have now, when will this happen? So for, yeah, like 10 years, 50 years, when should we expect to have this this shift in this elevation temperature? And then another question, which also may be interesting related to this aspect, is also how will rainfall changes? Because, for example, in the upper part of the catchment, we also have glaciers now, which are melting very fast, and they contribute to an increase in the discharge, especially in summer. What will happen once the glacier will be gone? How will rainfall affect the sediments that will be there to be transported away? So, like I said, this increasing in sediment supply is also contributed to the darkening of the glaciers. And once the glacier will be gone, then we'll also have more sediments there on the proglacial plain that could potentially be transported during the high rainfall events. So this is all very interesting, and I think it's worth to study this aspect as well.
Okay, there's another question by John Major, and I think it's related to what you talked about debris flows on the bias potentially in the record. The question is, how were debris flow occurrences identified? Did they have to get done to towns? And could small ones at higher elevations be underrepresented?
Yes, this is another problem, in fact. Well, this catchment is very much used, let's say. So there is a very touristic area. So I would also in summer, for example, there are many trails which go up higher up to the mountaintops and up to the glaciers. So I would say that for the most recent debris flows, also the very small one could be detected. But for sure, there is a problem related to the events that occurred in the past. How they are identified, honestly, I don't know. I think that they depends on if someone reports them, or of course, if they create some damage, they are reported. And otherwise, I think it depends if someone actually see them. So it can be that there is some sort of underrepresentation. Yes.
Okay, so we have another question related to sediment discharge. This one is from Oliver Francis. If you have any idea whether the sediment discharge leaving the catchment has changed due to the climate, to the change in sediment supply.
It depends on the time scale that we are referred to, because in the catchment there are some of my colleagues which are monitoring the sediment transfer since 2014. For example, we know this is not published yet, but the preliminary results indicate that major sediment occurs during the summer season because of glacier melt. So there is an increase in sediment transport due to the melting of the glaciers, and also during very extreme rainfall events. But then if we look at the larger time scale, then well, this is actually still in progress, because I also have samples with I sampled with cosmogenic nuclides in these catchments, but I'm still waiting for the results. So this could give us some idea of how erosion has changed in a longer time scale, but unfortunately I don't have the answer yet.
Great. Okay, so we have another question from Brent Ward. He says, interesting talk. If thawing permafrost is triggering landslides, do we need to consider frost cracking? The rocks are already cracked, but the thawing would allow release.
Yes, exactly. Frost cracking is, as well as also permafrost, is like preparing the rocks to failure, let's say. It's like a factor that can be considered as a preparatory factor. And then we could either have gravity or snow melt or precipitation, which are going to then be the real trigger for the event itself. Yes.
Okay, any more questions, anyone?
I have one, in case nobody has. Maybe I missed that, but I was wondering, with the data set you have, Sara, are you able to identify or to investigate kind of the landscape memory effect over this time case? Meaning that if you have one detachment event, will this promote or not another event in the next years also, or nearby event? Is it something that you could explore?
Yes, in fact, well, I did not mention here, but if you look at the paper, there are all the numbers related to the like the geomorphic domains, and if I remember correctly, I think that the areas that already show signs of instability are at the second place in terms of location of new detachments. So this means that the areas that are already unstable also favor more instability for the future. And also for these areas, it is possible that new detachments occurs with lower intensity events, rainfall events. This was a case analyzed by a landslide that was generated on a rock glacier. For example, there was a huge collapse of the rock glacier front in 2014 in relation to a heavy rainfall event, the same that also triggered many debris flows in the catchment. And then in the following years, both in 2015 and 2016, the same location trigger new smaller landslides, and we think it's just because of a bigger one in 2014. So the rainfall event itself was not very strong. In fact, did not trigger any other events in the catchments, but was able to destabilize this portion of the basin.
Okay, thanks. I'll look into the paper then.
All right. I think so. This is it for us. I want to thank everybody who joined us today. I want to thank Sara again for her really, really interesting talk. And I hope you all will join us again next week. And yeah, that's it.
Thanks to all.